Okay, let's continue. It's 21, right? Yeah. So, in the last class, we started to see the motivation for differential signals. Again, the main reason is in a single ended scenario, your circuits are immune to any kind of variations in supply, ground, and any kind of interference. Whereas if you have differential signals, that gets cancelled out. And even there, we saw difference between pseudo differential and fully differential. In a pseudo differential, your circuit is sensitive to common mode signals also, or in other words, it has a bad common mode rejection ratio. In a fully differential case, the common mode gets rejected. And in particular, when we try to make this fully differential amplifier, we recognize that the output DC or the output common mode doesn't get set automatically. Now, although in our two-stage single-ended op-amp also we had a similar scenario, there the global negative feedback took care of the biasing. But here, because we have two voltages, that is two virtual ground voltages Vx and Vy, one single global negative feedback is not sufficient to take care of it, because that ensures that the differential signal is set. Now, in addition to the feedback for differential signals, we argue that we also require a separate feedback for the common mode signals, and that's the requirement for a common mode feedback loop. And we also started to see how we can make it. The idea is again simple. The common mode here is not defined in the first place because we have two current sources biased independently. So the goal is to make sure that one of the currents is biased independently and the other current source is biased based on the independent one. So here we have PMOS and NMOS. So we can assume that we are fixing the current for the NMOS, and then we'll go and tune the current in the PMOS to make sure that the current here matches the current here. That's the idea. And for that, we have to sense the error in the current in the PMOS and the NMOS transistor. And it might seem that we have to look at this voltage, but remember that we are not interested in the actual voltage and the actual currents. We are only interested in the common mode voltage and common mode part. So instead of looking at the voltages separately, we look at the common mode of the voltage. And using the common mode, we sort of compare the common mode with the reference voltage, say half the supply. And then we go and tune this. Right? And that's what gave rise to this structure. And this is what we have. So let's continue from this. So let me erase all this. Let me redraw this. So this I'll call as VO plus and VO minus. So here there are two blocks to be determined. One is this fellow that detects the common mode, and this is the op-amp that we already know how to make. So let's look at how to make this fellow. So I have two voltages, VOP and VOM. How do I get the common mode of the two voltages? What is the operation I should do mathematically to get the common mode? I should take the average. So this complicated looking common mode detector is just a block that takes the average of two voltages. And what is the simplest way to take average of two voltages? How do you average using resistor? Let us say I have VO plus, VO minus. What do I do? Yeah, I think you guys understand. So if I have two identical resistors kept like this, the midpoint is going to be the average of the two voltages. So that's one trivial way to make this. So I'll replace this block. So this is going to be an EOC. And then you can go and connect it to the op-amp and it's done. So I'll call this RCM and RCM. Is that okay? So again, now we can clearly see, for example, let us say the bias current or the common mode current in the PMOS transistor. Let me mark it as IP. If the DC bias current of the PMOS transistor is greater than I0 by 2, which is the DC current flowing here, what can you say about the common mode voltages? Yeah, if I'm pushing in more and more current into the output node here than the current that is being drawn out, both the node voltages will increase, so the output common mode will increase. Now let me mark it. So which means VOCM increases. As a corrective action, what should I do now? I should decrease what? I should decrease the PMOS current. And how do I decrease the PMOS current? Yeah, so I'll say need to decrease IP, which means I have to increase the gate voltage VBP. And as you see, if VOCM increases, this voltage also increases. The feedback is working fine. So let me have this. Let me erase this. Is this clear? And of course, one trivial way to make a common mode feedback is this. See, I see that if my VOCM increases, I have to go and increase the gate voltage, right? That's what I wanted. So here I see that this voltage is increasing. I want to increase this voltage. What is the simplest connection I can make? I mean, if this voltage increases, I want to increase this voltage. Huh? What can I do? Yeah, one trivial way to do is I'll say this. I don't do the Opamp business. I can directly go and connect like this, and I'll say I'll not use the Opamp. Same thing again. If the output common mode here increases, the common mode increases. We need to decrease the PMOS current. We need to increase the gate voltage. This obviously happen. Okay. So this is one trivial way to make a common mode feedback. So if you think that I don't want to design more op amps, yeah, you can do this. And I'll draw this in a more aesthetically pleasing fashion so that it's nice to see. So this is the circuit we have with the common mode feedback. So what I'm essentially doing is taking the two outputs, giving it to a resistor. The midpoint of the resistor is connected to the gate. Right? So I'll redraw it like this now. Erase all this. What I'm essentially doing is this. Sorry. I'm having the common mode sensing resistor like this. The midpoint gives the output common mode, and what I told was I'm going to directly go and connect it. So let me mark it as RCM and RCM. So I'll call this as CMFB variant 1. So this is the simplest CMFB you can have. So now tell me what will be the output common mode in this case? That is, what will be the DC bias at the output? What do you think the output finally will, output bias will settle to finally? Okay, so if this is VOP, VOM, where is the output common mode in this? Where am I sensing the output common mode? Middle of this fellow. This is VOCM. So now tell me the gate voltage is the VOCM. So what will be the voltage to which this gate will settle to? VDD minus VSG of the PMOS transistor at what current? Is that clear? Because the entire feedback loop is trying to make sure that the current in the PMOS transistor matches the current flowing bottom side, which is I0 by 2. So the loop will make sure that the gate voltage is set to this value. And in this particular CMFB, the gate voltage is same as your output common. So this is the voltage to which the common mode will settle to. The SGP at a current of I0 by 2. Is that okay? Of course, we can also see it if you look at the common mode picture. Let's look at the common mode scenario where I am applying a DC voltage on both sides. So if I apply equal voltages at the gate, what can you say about these two voltages? They'll be same. If these two node voltages are same, what can I do? Yeah, can go and short it silently without telling anyone. Now I can draw the half circuit now. So let me draw the common mode half circuit. So I'll have the two PMOS transistors put in parallel. Similarly, I have the two NMOS transistors put in parallel, and I have the tail current source here, right? I'll say it's 2x. Now what happens to the resistors? They'll also they are also getting put in parallel. So from here I have the resistor values RCM by 2. One end of the resistor is connected to the drain, the other end is connected to, yeah, so it's going to the gate like this. Again, remember the what I have drawn is valid even for DC and large signals, because this entire business of shorting the two nodes just relies on the assumption that if I apply equal voltages on the gates, I'll have equal voltages at the drain. That is true for large signal, small signal, anything. Now it's clear that this is the the output common mode is this. This is the gate voltage, so this will get set to VDD minus VSG at the required current. Is that okay? Now, of course, on top of this DC bias, if I have a small signal common mode excitation, now we can draw the common mode equivalent circuit of this fellow, and then calculate how much the small signal voltages are that we have done before. I'll not do that. Hope this is clear. Okay. So now this is, at least now we know the common mode is getting set to a defined value, not arbitrary. So hopefully the circuit will be biased fine. But remember that our main goal is to not worry about common mode gains. Our main job is to make some block which has a large differential gain, right? This common mode business is a side quest that is required to make sure that the transistors are all biased properly, correct? Now let's actually check if the differential mode picture is fine. So let me say that I have now differential signal applied like this, minus VID by 2 and plus VID by 2 on both sides. Now how can I simplify the circuit for small signals? Sorry? Yeah, so how can I simplify? Yeah, the voltages along the line of symmetry will be 0. So which means all of these nodes will be at small signal ground. So let me draw the differential mode half circuit then. But remember, this half circuit I am drawing is only for small signals, right? Because the point that the nodes along the line of symmetry will be at ground is true only if the circuit was linear, and only for small signals this fellow is behaving like a linear circuit. So let's draw the half circuit. So again, source is incrementally ground for the PMOS. This is fellow. The NMOS is here, and the source is ground. And I'll take only one half. So this is VID by 2. So I'll call this as half the output, right? Or I call it as VO plus, doesn't matter. Now what happens to the gate of the PMOS transistor here? Where is the gate of the PMOS transistor? It is at small signal ground. Remember, this is along the line of symmetry. The gate is at small signal ground. Right? And what can you say about the resistor RCM? What happens to that? Yeah, it is going to be connected from the output. Is this fine? How I have drawn the small signal half circuit. So now tell me, what is the differential mode gain here? What is the small signal gain in the circuit? This is very difficult to say. What is the small signal gain here from the input to the output? minus, yeah, minus GM2. Short circuit GM is coming from this fellow. The output resistance is how much? R naught of 2, R naught of 4 parallel. This is going to be the differential mode gain. Remember, VOP is basically one half of the output. So the gain from VID by 2 to VOD by 2 is this. So which means the gain from the actual VID to the actual output is the same. Okay. If this is confusing, you think of it this way. Remember, if this is the if I call the gain here as some AD, my VO plus is AD times VID by 2. What can you say about VO minus? That is going to be the negative of this, right? Because that's just the other half circuit where the input is negative, so output will just be negative of this. I take the difference between the two, that is what is my final output, differential output. That is basically the same gain times VID. So if it's not clear, I'll remark it here. So this means that my final output is basically the difference between the positive and the minus outputs. This is basically the gain times VID. Okay. So now straight away we can see if, let us say, I don't want my common mode, whatever I do for the common mode, if that should not interfere with my differential mode operation, what is the constraint I have now from the gain? RCM should be large compared to what? Yeah, RCM must be much greater than I'll say the intrinsic output resistance, right? That is basically R02. So you have to choose my common mode sensing resistor to be significantly large compared to the existing output resistance, so that it does not affect my small signal differential mode gain. Because this is what we are finally interested in, and we should not be impacting this. Okay. Is it getting recorded? Yeah. Anyways, so this is the simplest common mode feedback. Here, although the common mode is getting set to a value, that value is not completely under your control. It is VDD minus a VSG. Now this VSG can vary based on the threshold voltage variation, mobility variations, and so on. So if you want to have a better control on the output common mode, so you have to actually go and use the Opamp. There is no other option. You basically have the Opamp to compare the output common mode with the required reference value and then do it. So let's see how that's going to look like. Yeah. Yeah. Why do you avoid using resistors? Okay, that is actually, I mean, you're confusing with inductors. Inductors occupy a lot of area. So only at extremely high frequencies you can make inductors on chip. But resistors are pretty fine. There is no issues. Uh-huh. Yeah. The idea is you can't make a really, really large resistor. True. I mean, there the reason was not the fact that we can't make large resistor. I think you're confusing it with the fact that in a normal diff amp, I don't know if this is what you are hinting at. Where did I have it? I think I talked about it here somewhere. Yeah, in this fellow, what is the problem if I increase the resistance value here? It is not because, the drop will increase and the transfer will not be in saturation. That is the problem. It is not because I can't make large resistor. You can actually make large resistors. It's not a problem at all. You cannot make crazy large resistors like 1 tera ohm, 10 tera ohms and so on. But few mega ohms and hundreds of mega ohms you can easily make. So yeah, so let's see how this circuit is going to look like, where I'm going to use an op amp. So let me erase this. So you cannot escape from the op amp now. You have to design one and use it. So let me. So here again I have an op-amp which takes in 2 inputs gives 1 output. What is the simplest realization for this? The 5 transistor OTA, that's the simplest thing, so we can use it. So let me replace it with the 5T OTA. So let me push it here. So let me quickly draw the 5T OTA. Erase all this. So I make the diode connection here. This is going to be my output. So let me connect it back. So the output of the op-amp controls the gate bias. Now I have the inputs. Let's figure out what should be connected where. Right? So this is the output. If this is the output, what is the plus terminal? The left side or the right side? Left side, because remember, if I increase the gate voltage, what can you say about the drain voltage here? From gate to drain, there is always an inversion, right? So which means the left side is going to be negative. Sorry, right side is going to be negative, left side is positive. And here you see the negative is connected to the reference VDD by 2. So I'll connect this to the reference common mode, which is, for example, VDD by 2. And the positive terminal connects to the output common mode. The output common mode is here. So I'll directly go and connect it like this. Is this fine? There's all the unnecessary stuff. Is this clear what you have done? You have same thing. I'm sensing the output common mode using a resistor and then giving it to an op-amp, comparing it with the reference common mode, for example VDD by 2, and then going and tuning the PMOS current. Cool. So now look at this circuit. For common mode, at least what I have is this. I have, let me draw this. Okay, let's see first. We give this name. So let me call this common mode variant 2. So let's actually draw the common mode half circuit and see how that's going to look like, so that we get a better understanding. Again, for common mode, the assumption is I'm giving equal excitations on both sides. So as usual, these two nodes will be identical. So I can go and short them. If I short them, once again the transistors are going to get put in parallel. Right? So I'll erase it here and draw it directly. So I'll have only one PMOS here, size 2x. Similarly, I just have one NMOS. That is also size 2x. And what happens to the resistors? That becomes parallel. So let me know if it's not clear. I have just taken the same circuit. I assume that I'm applying a common mode excitation, let us say a DC bias for example, which means the drain nodes will be identical. I'm basically shorting the drain node so that the PMOS and NMOS are in parallel, and same happens to the resistor also. So this is the common mode equivalent circuit. Now look at this circuit. So here I seem to have a 5 transistor OTA here. The output of this goes to gate of another transistor, and the output is tapped from the drain and fed back. So if you look at this, does it remind you of something that you have already seen? Sorry, why gain boosting? It's a two-stage OTA because see, I have a 5 transistor OTA. The output of this fellow goes to the gate of another transistor, and I'm tapping the output from the drain. So what configuration this is? Input at the gate, output from the drain. What configuration is this operating? Common source. So this is one 5T OTA. This is another common source. I'm putting in cascade, and the final thing is put in feedback. If I were to sketch it, this is how it's going to look like. So the 5T OTA I am drawing as a block like this. Let us say some GM1. So the output of this goes and excites another common source amplifier. So I'll draw that in white. Let us say that is a minus GM2. And the output of this is connected to a resistor RCM by 2. So we'll make some space here. So the output is connected to an RCM by 2 resistor. And the output other end of the resistor is connected back to the positive terminal of the first stage, right? Because remember, this is a positive terminal, negative terminal. That's how we define. This is the equivalent circuit we have for common modes. Let me make it clear. This is the common mode equivalent circuit. Is this fine? So of course, at the negative end, we apply the common mode reference. So let us say that is some VCM ref, which is this fellow. So the hope is that if things are working, these two voltages will be equal, and the output is your output common mode that will be set to the required VCM ref. Right? That's the hope. But now, from your experience, you tell me I have a two-stage OTA. I am directly putting in negative feedback. So is it okay? Again, two-stage OTA, the moment I put in feedback, stability is not guaranteed. Correct? So I have to stabilize it. What is the simplest way to stabilize? I can put Miller. I can use Miller compensation. So what do I do for Miller compensation? Across the second stage GM2, I go and put a capacitor. I'll call it CCM because it is for the common mode picture. Is that okay? So which means in the actual circuit, where will the capacitor come? I mean, it is clear that we have to put the capacitor across the second stage, right? So here, what is acting like the second stage? I mean, the left side portion or the right side portion? Left side portion. So where will I put the capacitor now? Gate and drain of which transistor? This top one, middle one, bottom one. Top one. Now again, just to clarify, remember that our actual differential amplifier is still a single stage OTA. Right? This is still a single stage OTA. But it turns out to stabilize the common mode for this single stage fully differential OTA, I need to have another amplifier, which means for common mode signals, this overall combo behaves like a two-stage OTA. Right? So the compensation you are doing is only for the common mode signal. The differential mode part is still a single stage OTA, we'll verify that. So there we don't need to do anything. But it turns out to stabilize the common mode for that single stage OTA, you end up using an additional amplifier. So for common mode signals, you have an effective two-stage structure. Okay. So that two-stage structure for common mode needs to be compensated, and that is what we are doing here. So basically what that means is, if you don't do the compensation, so anytime you have a common mode excitation or common mode jump, the common mode outputs will swing or ring large. But if you take the differential part, it will be fine. But just that the common mode part or the actual individual outputs will show a lot of ringing. But if you take the difference, you might be fine. But this is also not something good, because if this starts to ring, transistors can easily go out of saturation here and there. So this is something not you want to have. The common mode needs to be defined properly, and that is why we need to have the stabilization. Is that part clear? Cool. So of course, this is something we can do, and As I mentioned in the last class, sometimes if let us say the gate parasitic capacitor is causing an issue, what is the simplest fix to take care of this? Yeah, we can in this the moment you have an additional gate parasitic capacitor, you have a delay in this path. To counter the delay, you can go and put a capacitor here. I'll call it CMZ because it is the 0. Something we saw in the last class, same thing you can do. So which means in the actual circuit, the capacitor will come in parallel to the resistor like this. Okay. Now, of course, this is only in the common mode picture. Now we need to add the same capacitors in the actual circuit, right? So let's see how that's going to look like. So if I look at the main Miller capacitor, that is in the common mode equivalent circuit, it is getting put across the PMOS transistor, the 2x PMOS transistor in parallel. So in the actual circuit, how should it come? In the common mode picture, I have two of the PMOS transistors put in parallel, and I have one single capacitor, CCM. So in the actual circuit, how should this come now? I need to have two capacitors put across both of the transistors. Correct? If I put the two in parallel, I should end up with an effective capacitance of CCM. So the individual capacitance value must be CCM by 2. Again, reminding you that this is the compensation capacitor only for common mode. Your actual differential amplifier is still a single stage OTA that we'll verify when we look at the differential behavior. Now, of course, we also had this zero adding capacitor that is actually put in parallel with half the common mode resistor. So in the actual circuit, what should happen? In the common mode equivalent circuit, I have RCM by 2 and one capacitor put across it. So which means in the actual circuit, what should happen? I should have two capacitors. Very good. What should be the value of the capacitor? Half the original value, CCM Z by 2. Here also I'll have CCM Z by 2. Okay. Again, this is not necessary that you need to have the 0. In case the gate parasitic capacitance here is causing an issue, you add this. Great. So yeah, one last thing. So let me copy paste this. See here, when we looked at the CMFB, we started off with the goal of having an Opamp, right? This Opamp is what we realized as this fellow. Now, the simplest realization was the 5 transistor OTA. How many different variants are there for the 5T OTA? Is this the only way to make the 5 transistor OTA, or I can have different circuit implementation? Yeah, here I used an NMOS variant. I could also have used a PMOS variant. So the question is, do you think using a PMOS variant is better, or this is better? How will you determine? Sorry? Why? Yeah, gate voltage is VDD by 2, but VDD by 2 is half the supply, right? Both NMOS and PMOS will be equally fine. I mean, but you're going in the right direction, right? Because for small signals, is there a difference between an NMOS variant or a PMOS variant? If at all there is a difference, where should that be in? Large signal or DC biasing, for example. So here, if you look at the gate voltages, as I mentioned, it's half the supply. That's typically okay. So what is the other thing I can look at? Maybe if you look at this common mode equivalent circuit, it is clear. The gate voltage is fine. What about the drain voltage? What will be the drain voltage here? sorry, what will be the gate voltage here for this transistor? What will this voltage be set to? Yeah, VDD minus VSG of the transistor at of the PMOS current at PMOS transistor at some current I naught by 2 something. Okay, which means the output of the first stage should be this value. Now tell me whether this is better or I should replace with the PMOS transistor. Why this is better? So this voltage helps me, right? This is VDD minus VSG of a PMOS transistor at some current, right? Yeah, correct. As he mentioning, even for this voltage would be some VDD minus, I'll say VSG of some PMOS transistor X at some current Ix. I call this 2 times Ix. Correct. So as you see that, as you see clearly, if I have an NMOS input pair, seems like the voltage here is naturally at a value that is compatible with the second stage. This is something we saw in a 2-stage OTA, right? If your input pair is PMOS, you are better off with the second stage being NMOS. Vice versa, if the second stage is PMOS, a better option is to have an NMOS as the first stage. Same thing. Okay. Now, another thing again related to the 2-stage OTA we discussed before. Remember that this voltage is getting set to VDD. Let me label transistors. Let us say M3, M4, M1, M2. So what is the drain voltage here getting defined to? The drain voltage is the gate voltage of this. What is this? VDD. VSG of which transistor? M3 or M4 at what current? I naught by 2. Great. Let me call this 2Ix. What can you say about this voltage? VDD minus, let me call this MCMD. VDD minus VSG of MC at what current? Correct. Now, if I choose these two VSGs to be not equal, what can you say about the drain voltages? They will not be equal. If the drain voltages are not equal, what can you say about the gate voltages? So, which means the output common mode here will not lock to this value VDD by 2, but it will be VDD by 2 plus some offset. And what was that offset called? That was a systematic offset we again discussed with the 2-stage OTA. So, to prevent systematic offset, how should be the design choice now? Yeah, both VSGs must be equal. So, what does it boil down to as a design choice? Yeah, current densities of all these transistors, let me just put a dot. All the PMOS transistors should have the same current density. Correct? Or maybe I'll put a circle so that it is clear. All of these must have the same lookup table parameters, same current density, right? Because remember, if I fix the length and one of the parameters, everything is frozen. So here, all of them will have the same length and same VSG. So which means current density, all other GM by ID will be same. So same thing we saw for a 2-stage OTA will hold good here. So when you are designing the CMFB, this is something you should take into account. Great. So as of now, we have seen only the common mode equivalent circuit. Let's actually see what happens if I apply a differential mode circuit. Differential mode signal. Let me copy paste this. So for differential case, I am applying, let us say, plus VID by 2 and minus VID by 2. So how will this simplify now? How do you solve for this now? Same as before. All these nodes along the line of symmetry, they will be at small signal ground. So now look at this. This gate voltage, small signal ground, correct? That is same as this fellow, correct? And remember that this is also along the line of symmetry. All they have, I've just bent it and drawn it horizontally. This is also along the line of symmetry, correct? So this is also at small signal ground. Is that clear? And DCMRF is also a DC signal. For small signals, that is also ground. Now you see that this fellow inputs are shorted for small signal, output are also shorted for small signal. So what can I do to this? Yeah, I can basically completely ignore it. So I'll erase it here itself. Right. Okay. So of course now even the common source is not, this terminal is also going to be small signal ground. Okay. So which means if I simplify this, I'll just have this half, I don't have to worry. I'll take only one half. This is what I effectively have. Is that okay? Again, the argument was this entire OTA for small signals, if we apply, if I apply differential mode, this OTA is not playing a role. This node is along the line of symmetry, this is grounded. I just take one half of the circuit. And that's basically this. So let's redraw this nicely. So the differential mode, small signal half circuit. This again for small signals. Okay. So I just have the PMOS transistor. What can you say about the gate of the PMOS transistor? That is small signal ground. Have the NMOS transistor. I apply, let us say, the ID by 2 here. So what else I have in addition? The common mode sensing capacitors, resistors. So I have RCM here. I also have this capacitor CCM by 2, the Miller compensation capacitor. That will also come here. CCM by 2. And what else? This zero adding capacitor is also so of course as before. Now you see that this RCM resistor is going to load the DC gain. So what is the DC gain? If I call this M2, M4, can you quickly tell me? This is V out. Differential gain is minus GM2 into same thing. R02 parallel R04 parallel RCM. And what else? Yeah. So which means once again my RCM must be much greater than my intrinsic output resistance. Correct? And let us say you had a load capacitor also here to start with. In the differential mode, let us say you had a load capacitor. Now what can you say about the unity gain frequency of the amplifier now for this? How will you find the unity gain frequency? Yeah, DC gain the pole location. So what will that come out as finally? GM2 by what is the total capacitance? CL plus CCM by 2 plus CCMZ. Yeah, thank you. Again, if I make a mistake, you know why I'm making the mistake. So now as you see, in addition to having DC gain being dependent on RCM, even your unity gain frequency seems to be affected by these capacitors. So you can't go crazy and put large caps to stabilize the loops. Should be careful. So when you're designing for your differential mode omega u, these also have to be taken into account. Should have sufficient margin when you're designing for your differential mode gain, so that you can have some leeway for adding capacitors for common mode feedback, that is for stabilizing the common mode feedback. Is that clear? Great. So this variant of common mode feedback is again very commonly used, but as I mentioned, one of the main drawbacks is the fact that this RCM is coming and impacting your output resistance. Now, if the output resistance was not very high, it is okay to have RCM larger than that. But let us say you have a cascode here, which means the output resistance must have been very large to start with. So having an RCM even larger than that might become very impractical. Right? So that's why we have other variants to take care of that. So let's look at that. So this is what we have. So here again the idea, the problem is that the resistors we have here are loading the output nodes. Right? So let me remove the capacitors. We know that we can add them. Right? So if you don't want the resistor to load the output nodes, what can I put in between? I can basically try to put a buffer. So what is the simplest way to make a buffer? Common? So let's try to do that, right? So basically the idea is you don't connect the output to the resistor directly. You add a voltage buffer and then do it, and that is done sometimes. So let me just show how the circuit will look like. First let me draw the voltage buffer. So I am drawing a common drain, simple common drain. So the outputs will be tapped from these, and I'll add the resistor at the output of the buffer. Okay, this is RCM. Let me call the currents here IA. So now tell me if I have the total voltage at the input of this buffer is VOP, and similarly the total voltage at the input of this buffer is VOM. So the input here is VOP, that is given to the gate of the transistor. What can you say about the voltage here? It's going to be VOP minus VGS of the transistor but I. Similarly, you look at this fellow, it takes in an input VOM. We are tapping the final output from here. So this voltage will be VOM minus VGS of the transistor at a current IA. So which means the actual common mode you are sensing, how much is that? Sorry. So what will be this voltage? Average of both of them, but how much is that? That is the actual VOCM you want, VOP plus VOM by 2. In addition to that, you have, correct? So which means now your common mode feedback is trying to make sure this voltage is equal to this voltage. So which means now your VOCM is not equal to VCM ref. It is equal to VCM ref plus that VGS, or I will say it is making VOCM minus VGS at that current to be equal to the VCM ref. And of course this is not what you want, right? So what is the simplest fix for making sure that my VOCM is set to VCM ref and not VOCM minus VGS? Why? Yeah, the idea is you put another buffer here, so and make sure that this is not getting equated to this, but instead this is getting equated to VCM ref minus VGS. Fine. So basically you add, don't feed the VCM ref directly, you buffer that also. You feed VCM ref here. Okay. Now this voltage will be VCM ref minus VGS at that particular current IA. Now these two will be made equal yourself. Okay. Now this I'll call it as variant 3. Now there is another variant that is commonly used to avoid the loading of the resistors. Right? For that, let me actually copy paste the old circuit. But before that, is this clear what we have done? I've just basically, to avoid the loading of the resistor, we have introduced a voltage buffer that was introducing a voltage drop. So basically, you introduce other voltage drop. Nothing great. You and your friend had 5 chocolates to begin with. You drop 2 chocolates. You have only 3 chocolates. To make it equal, you make sure your friend also drops 2 chocolates on the ground. It's a silly idea. Oops, not this. So let me just move on to the other. Yeah. So this is our main circuit. So here is where we wanted to avoid the resistive loading. Let me remove the caps. We can add it later. Yeah. So the idea here is the following. So let me call the small signal voltages here as VOP, VOM. So the small signal voltage here is going to be VOP plus VOM by 2. Fine. If I call this voltage as Vx, what can you say about the current, small signal current here? It is some, I'll call this, so let's say some GM times VOP plus VOM by 2. So if you see what's happening from the terminals here to this current, we are first taking the voltages, first averaging the voltage and converting that average to the current. Right? So two operations, we are averaging and converting it to a current. Now both are linear operations. So what can I do now? Instead of first averaging and converting it to a current, what can I do? I can first convert it to a current and then take the average. The idea is, averaging in current is easy because averaging is adding quantities. Addition of currents is simple. You just put two wires here. KCL will ensure that the currents are added. So that is what is done. And the way it is done is this. If I just massage this equation, it becomes apparent. So I can rewrite the equation like this. This GM times VOP minus Vx by 2 plus GM by 2 times same. So which means now I don't want to have the resistor. That's the whole idea, because it is loading me. And if I somehow make sure that this particular current is flowing in this branch, I'm fine. So this current comprises of two quantities. Now I have to generate a current proportional to VOP minus Vx. What can I do? I have VOP here, Vx here. I want to push in a current which is GM times this. Yeah, I should use a MOSFET. So where will I connect the gate and source to? Source is connected to Vx. That will push out the first part of the current. Of course, GM should be GM by 2. That will come to it later. That we can adjust the sizes. Similarly, to generate this current, what do I do? Another MOSFET. Now I have to add the two currents, right? I have generated two currents. I have to add them. What do? I just use KCL. Now the last part of the puzzle is to make sure that the GM of these transistors is 1/2 compared to the GM of this transistor. So if this has a size of W, I'll make sure that these are sized half to get the required GM. So this way we can avoid any kind of resistive loading because we are directly connecting gates of the transistors, so you will not have resistive loading. But of course the gate capacitance will be there, capacitance loading will be there. That is something you can't avoid. So I'll call this variant 4. So to summarize, we saw basically 4 variants today. So the first variant was simple. You have the common mode sensing resistor and directly go and connect it to the gate voltage without using an Opamp. The second variant is where you use the resistive common mode detector and then use an Opamp. Third is where we decided to avoid the resistive loading. So which means you added a buffer correct? Yeah, you added a buffer and did this. I will not show. I will say, and then you did this. And the last variant is where we saw instead of adding the averaging it in voltage, we averaged it in current by using MOSFETs like this. Correct? Of course, so many options are there. We need to understand what is good in which scenario. Now, now can you tell me in what might be the drawback of this compared to this? Having a resistive common mode detector like this directly, what is the drawback of this? That is going to negative side is going to be resistive loading, and whereas here there is no resistive loading, right? Now, of course, see, downside with this is the following. See, in these three, in the variants 3 and 4, the output is directly connected to the gate of a transistor, be it here or here. The output is connected to the gate of a transistor. Ideally, you want the output to swing very small or very large. Let's say this is the fine output stage of the OTA. The output is going to swing large, which means these transistors can go out of saturation, which means these transistors will impose additional constraint on your output swing limit. Correct? Whereas in the other variants, the output was directly connected to a resistor. The resistor can handle any swing, it's okay, and only the averaged output is sort of fit here. Correct? So differentially it can swing a lot, but if you take the average, because it's, what I'm saying is you can have a VOCM plus a large VOCM minus a large VO. Individually this can swing a lot, but if I take the average, it's not going to swing a lot. So here it is better, whereas if I directly connect it to the gate of the MOSFET, it's a problem. So here I will say the plus is swing limits, the negative is the swings. Okay. So in the next 15 minutes before the class, we'll see how we can use all of this to make a two-stage OTA. Because whatever you have seen so far is basically a single-stage OTA, right? This is your main differential amplifier. It is still a single-stage OTA. We confirmed it by looking at the differential half circuit. Correct? Now, of course, single-stage OTA, what is the drawback? Single-stage OTAs, why did we go to... It cannot drive resistive loads, so that's when we go to two-stage. So I already have the two-stage OTA drawn here for simplicity. I'll just quickly show what, there's no, nothing majorly different. I have one single stage followed by a common source on both the outputs. This is a single stage fully differential OTA we have seen. The second stage is added on both sides. Now remember that. Let's first focus on the differential mode part. For the differential mode part, I have a two-stage OTA. Will it be stable if I put it in negative feedback? So I have to compensate this in the first place for differential mode operation. Right? So what is the simplest way to compensate? Miller. So I need to add a capacitor. Where will I add the capacitor? I'll put the capacitor across the first stage or second stage. I have two PMOS transistors here. So what will I do? Let us say I put this as well as a zero cancelling resistor I add. So this is on one side. What will I do to the other side? I should do the same. So this way at least the differential mode part is set. Is that clear? Now you can know the differential mode half circuit. You will have only this fellow and this fellow. Same as what we have seen, normal two-stage structure with the poles we have seen before. Now comes the fun part. So if I apply just the DC or common mode excitation, you think the common mode voltages will be defined here? Huh? No? What about the common mode voltages here? Once again you have two current sources biased independently, two current sources biased independently. So you should have a common mode feedback not just for the first stage but also for the second stage. So I'll just show it at a block level. Let us say you have a CMFB here for the first stage. This is, I'll call it CMFB for stage 1. I'm assuming that the NMOS current is fixed to a value and you're going and tweaking the PMOS current source by sensing the output common. Right? And similarly, you will have another common mode feedback for this. We'll come to that next. But the discussion I want to have is, we saw 4 variants for the common mode feedback, right? So first tell me, should I pick a variant from the left side column or the right side column for the first stage CMFB? Remember, the left side column are resistively loaded. They drop they can impact the overall DC gain. Right side has issues with swings. So now I'm looking at the first stage. So what do you think I can use? Why? So what he's saying is this. Remember that if you have a 2-stage OTA, maximum gain is coming from which stage? So which means the output resistance here might be very large. You might have a cascade, for example. So which means it will be difficult for you to have a resistor which is much larger than the output resistance. So that makes this not a great choice. But of course now you have only this to use. But here the option is the output swings. So now tell me, if I have a 2-stage OTA, let us say having 2 gains A1, A2, and I put it in negative feedback. So this is overall Opamp, right? At the output, you'll have really large swings. But what can you say about the swings here? How much lesser will it be? The output here will be A2 times smaller than the output here. So swings at the output of the first stage will not be really large. We expect that the swings will not be so much. So which means you can actually use either of these. Okay. So here that's why a preferred choice is to use, I'll just mention, CMFB1, use variants 3 or 4. Is the reason clear? Because I can't use resistive, I can't connect the resistor directly because the output resistance of the first stage might be really large, because that gives the maximum gain. So which means if you cannot have a resistor that's a common mode resistor that is much larger than the output resistor, you'll have to use MOSFET based CMFB. But there the swings are a problem. But as we mentioned, as we saw now in a 2-stage OTA, maximum swing is at the output, yes. But the output of the first stage, the swings will be smaller by a factor equal to the gain of the second stage. So which means you can nicely use MOSFET based CMFB. Of course, remember you have to feed in a reference for this. So I'll say VCM ref 1. So do you think I can use any arbitrary value for this VCM ref 1 or something else might dictate this? The output common mode, can I choose it to be anything or something else? Huh? Yeah, but I mean you can choose VDD bit, but is there something else that may put an additional constraint here? The output common mode or the output DC bias, the output DC voltage, is it also impacting something else? We are looking at this voltage, right? Remember, this is connected to the gate of the second stage. That is directly impacting your VGS. Now remember, for a differential mode operation, you would have designed the second stage to have some GM. And from the lookup table, you would have found that I need some particular VGS for this. Correct? So let us say you already designed this so that it carries some particular current, say I6 or something. I'll call this M5, M6. So the output common mode at the first stage, which is same as the gate voltage for the second stage, VG5, should be equal to what value now? It needs to be biased with the current I6. So what should be the voltage? VDD minus VSG of M5 at a current of I6. So you cannot arbitrarily choose it to be VDD by 2 or anything, because this is directly setting the VSG of your second stage. Okay. So from your differential mode performance, you would have decided that, hey, my second stage needs to have some GM, and you would have sized the transistor to have a particular VSG. So your VCM ref must be equal to this value. Correct? Now that begs a question, how do I generate a voltage which is equal to this value? Because in our CMFBs, you see that I have to go and feed a reference voltage here, right? For example, here. Where is it? This reference voltage, I have to feed it, which means I have to generate that voltage somehow. So how can I generate a voltage which is of this value? Sorry? We have a PMOS, okay, connected. Yeah. I basically have something like this, and if I short this is going to generate the required voltage. And remember, this PMOS transistor and this PMOS transistor, how should they be? They should be identical. If I do this, what is this voltage? This is the required voltage you have. Is this clear? And of course, the output stage might carry a lot of current. So just for generating this voltage, it doesn't make sense to burn equal current there. So in practice, we can basically scale this entire thing down by a factor of 10. That is, you scale the currents also and the width of the transistor also by the same factor. Current density doesn't change. Length is not changing. ID by W is not changing. So my VSG will also not change. Is that okay? Is this clear? This is the considerations you should have for the first stage CMFB. Right? So if your output resistance is really large, you might not be able to use a resistive based CMFB. Right? In that case, this is the option, use MOS based CMFB. And in either case, whether you use a resistive CMFB or MOS based CMFB, you need to generate a VCM ref, and that cannot be really arbitrary, because that directly sets the VSG for your second stage PMOS transistor or NMOS transistor, whichever you have. So you generate that voltage by having a biasing branch like this. Is this clear so far? So that is for the first stage. Now remember, even for the second stage, CMFB is not defined. So let's see what to do for that. So let's look at second stage. For second stage, I need to sense the output common mode. So here, do you think I can have the resistive ones or the MOSFET based ones? Why? Yeah, remember at the output, this is the final output of the OTA. You won't have really large swings. So which means using a MOSFET based CMFB is not really a good choice. You have resistive ones, but what about the resistive loading? Why? Yeah, we already know that in the multi-stage OTA, the maximum gain comes from the first stage. The last stage is only for driving the load, so the gain might not be really so much. So the output resistance might also not be really large. So I can use a large enough resistor. Right? So which means I will have something like this. I have, let me see if I can push it up. Let me just draw this for the sake of completeness. So I have one resistive based CMFB. So I sense the average using two resistors. Now I'll compare the output common mode with the reference. Here, what can be a reasonable value for VCM ref? Yeah, it can be VDD by 2, because this is the output stage. You won't have maximum swings from 0 to VDD. So it makes sense that you have somewhere in between. Now, in the for the second stage, which of the do you think I can control both the? For the second stage CMFB, do you think I can fix either of them and tune the other one, or one of them is already fixed? PMOS is already fixed for me. because it's directly connected. I mean, of course, you can do things to make that independent, but as of now, the PMOS is basically fixed. The only choice you have is to control what transistors gate voltage. So in this particular case, the PMOS current is fixed. We have to go and tune the current in the NMOS transistor so that the current here matches the current here. So basically, I'll do this. Correct. And again, remember, if I look only the second stage CMFB, I have one. This will be a 5 transistor OTA, and this will be a second stage. So for a CMFB, this is going to be a 2-stage OTA. So what should you do? Where should I put the Miller cap? If I call this M6, M7, can you be specific? So across these two, I'll say CCM2 for the second stage CMFB. Is this clear? So for the CMFB, for the common mode half circuit, this will act like the first stage. This acts like the second stage, and the feedback goes here. Right? This is only for compensating your CMFB loop, not for your main differential mode loop. The main differential mode loop compensation is happening here. I'll call it CCD. Cafe Coffee Day. Okay. Now these are there for compensating only for the common mode loop. Is it okay? Now again, as usual, if you find that this gate parasitic capacitor is causing issue, you go and put a capacitors here. Blah blah blah. And these are things that you already know. One last point about this. So that is about, let me just remark it, CMFB2. Okay. So I can depict here, I can use variance 1 or 2, resistive CMFB. Okay. And yeah, the important other point I want to address is this. So here, what kind of 5 transistor OTA I will use? NMOS input pair or PMOS input pair? What will that depend on? Remember that, I mean, it's generally in a 2-stage OTA. You make design choices based on the second stage. You decide the first stage based on the second stage or vice versa, right? Here the second stage is fixed. Second stage is NMOS based, NMOS input or PMOS input. If this is NMOS input, the first stage should be so again, if I have to quickly draw it, again, let me just once again draw this so that it's clear. This will be your PMOS input. PMOS input pair. So once again, if you remember that if you want to avoid systematic offset in this 2-stage OTA, you make sure that you have same current densities for these transistors. Same thing in a 2-stage OTA. This is the second stage, so which means these also must have the same current densities. Is that okay? So as you already see, I mean, I can't draw the full circuit in one page, right? So that's why I always say there is no point in memorizing circuits. By hearting circuits is basically almost useless. Only if you understand why each part of the circuit is present, why you decide to use that particular design choice for that particular circuit, only if you understand that, you will be able to sketch it. I mean, these things you should be just able to sketch it without by hearting, right? You should understand and sketch it. That's what I want you to. And again, this will be your final design project, designing 2-stage differential Miller OTA, right? You can reuse a OTA that you already designed, right? I mean, you already designed the first single stage OTA for, I'm sure, for your first project, that you can obviously use and make a 2-stage OTA, and even these OTAs you can use the same thing. And again, see, when you design these things, right, don't start with putting transistor level details for everything. You start simple, start probably by only considering, I would say first start considering only the differential mode part. Assume that you have ideal CMFBs. Simplistic, I would say, simplistic ideal CMFB is put a really large resistor and then do this. For simulation, it's okay. This will take care of, CMFB. Same thing, you can try something for the second stage also. So that way, you don't have to first worry about CMFB. Design the differential mode part and make sure for the differential mode case, you have the required GM, GDS, blah blah blah, phase margin, gain margin, phase margin, omega U loop, etc. Once that is done, then you can start, looking at how to make the CMFB. So please start. I'll put out the problem statement, but I would say, so start doing it immediately. You'll have about 4 weeks to do, right? This is 3.5 weeks to do. Till the ensum starts, you'll have the time. You have about 3.5 weeks, I believe. So I hope that should be sufficient. Right? So again, for the last project, I cannot have any extension of deadline because I have to finish submitting the grades. So if you submit late, next year I can add that grade. Right? That's what I can do. So please start doing it immediately because that's the only way you can start finishing on time.